Now let's look at the PCB layout for the comparator-based nightlight circuit. At the moment this project is unsaved, so I will simply save it by going to File, Save Project As, and save in a location and with a name of my choice. Enter the PCB layout tool using the button at the top. Click on the Parts Manager button, which is in the same position as in the schematic capture window, and place the parts by clicking once, position and orientate, and then click once again. The part I'm going to focus on in this example is the op-amp. The op-amp is contained inside an 8-pin package called a Duel-in-Line, which looks like this in reality. There can be multiple amplifiers contained in a single chip. For 8-pin chips, this can be single or dual. Chips containing 4 op-amps exist, known as quads. These require more pins and so are contained in 14-pin Duel-in-Lines, which look like this. Apart from being longer and with more pins, all other dimensions are the same as the 8-pin Duel-in-Line. If there is only a single amplifier contained in the chip, then the pins are broken out like so. And if there are dual amplifiers contained in the chip, then the pins are broken out like this. The MCP602 is a dual op-amp chip, so there are 2 op-amps inside this single chip, and the pins are broken out like this. In the schematic capture window, the component identifier has the letter U for integrated circuit, followed by a 1 as this is the first integrated circuit in the design. Because there are 2 amplifiers in the chip, this identifier has an additional term A to denote that this is the first amplifier in the chip. The non-inverting input is pin 3, the inverting input is pin 2, and the output is pin 1. You can see from the pin diagram that this is amplifier number 1. If I place a second amplifier, the identifier has a B to denote that this is the second amplifier in the chip. The non-inverting input is now pin 5, the inverting input is pin 6, and the output is pin 7. You can see from the pin diagram that this is now amplifier number 2. If I then place another op-amp, this moves to a new chip, so the identifier now shows as U2, to denote that this is the second chip, and A to show that this is amplifier number 1 in that second chip. Placing another one shows U2B, meaning amplifier number 2 in the second chip, and so on. As stated in the previous example, provision needs to be made for a real-world power supply. Again, I will use wire connections, so I will simply find and place a pin to connect the wires to. Op-amps can be sensitive to noise on the supply rails, so I will add some decoupling capacitors on the supply rail to filter the noise away. This is especially important if the op-amp is being used in a low noise or high gain application. In order to filter out a wide range of noise frequencies, I will use a 100 nanofarad in combination with a 4.7 microfarad. The 100 nanofarad will filter out the high frequencies, while the 4.7 microfarad will filter out the lower frequencies. In the PCB layout, I will add my ground and power planes. In the previous example, I used the top and bottom side planes for 5V and ground respectively. In this case, the op-amp has decoupling capacitors to reduce noise on the power rail, and the routing of the power track becomes more important, so I will make both top and bottom planes function as ground for this application. The decoupling capacitors should be placed as close as possible to the op-amp supply pin. The longer a track is, the more noise it picks up from the environment. The capacitor filters the noise off the power rail and makes it clean. If the length of the track between the capacitor and the op-amp supply pin is long, it will pick up new noise from the environment before it reaches the op-amp. We can now connect the tracks. In this example, I will show you how to set net classes for track widths. This will automatically select the track thickness depending on whether it's carrying power or signal. I will also show you how to place a wire. A wire allows you to switch between layers while routing. Remember, blue is the bottom side copper and red is the top side copper. You can switch between them as you go by pressing the spacebar. Enter the design rule configuration by clicking the button as shown. Under the Net Classes tab, the two types of track are shown on the drop-down menu. In this case, there are only two options, power and signal. In the schematic capture, any lines which have a power or ground flag attached become power rails, otherwise they are classed as signal lines. If you have a line which you know will carry power but does not have a power flag attached, you can flag it as a power rail by right-clicking on the wire and placing a label with the command strat equals power, like so. Back in the net class settings, you can set the power tracks to be larger than the signal tracks. I will set my signal tracks to be 10 thou, or 0.25mm thick, and I will set my power tracks to be 20 thou, or 0.5mm thick. These choices depend on various factors, such as how many tracks need to be routed. If each track is made smaller, then more tracks will fit in a given board area. The thickness of the power tracks will also depend on factors like how much current they're expected to carry. Higher currents will require a thicker track. A necking thickness can also be specified. Necking occurs when you try and route a track through a narrow gap that it will not fit through at its normal thickness. The neck thickness is set smaller than the normal thickness, and the track will be shrunk to that thickness when passing through a constraint such as between closely spaced pads. I will set this to 8 thou, or 0.2mm, but again, this depends on various factors relating to the intended application. Now I enter the track routing mode, and I can begin placing my tracks. You see that any tracks flagged with power are automatically sized up to 20 thou, while the signal tracks are sized at 10 thou. You can go to Tools and disable the automatic trace style selection, and this feature will be turned off. I can then select the track sizes manually as I go. If a track cannot reach its destination due to obstructions by other tracks or components, then it can be routed through to the other side of the board using a via, and continue on from there. A via is a small hole drilled through the board and plated with copper to conduct the signal through. This allows the track to continue its route on the other side of the board. To place a via, double-click whilst routing, and the wire automatically switches layer. If you're on the bottom layer, it will switch to the top, and if you're on the top layer, it will switch to the bottom. The track can switch layers multiple times if necessary. We can open the 3D rendering tool by clicking on the button at the top and have a look at the finished board.